Alright, so like we've done in the previous videos, we realized that a lot of these equations can be used to model different types of real-world stuff. So exponential and log equations can be are used often to model scientific phenomena, and we're just going to look at a few of those here. First off, we're talking about Newton's law of cooling, which if you ever take a physics class, I'm sure we will talk about a lot. Also maybe in a chemistry class. And then finally, in the second example, we're going to talk about earthquakes and magnitude and stuff like that. So keep that in mind. Alright, so Newton's law of cooling, pretty much here's the formula for it. T of O is the initial temperature of this stuff. So most of the time we're going to think about a soup or something. T of R is the room temperature. R is a constant, and that constant is going to just depend on whatever you're talking about that's cooling down. E is just E, the number that we talked about in the earlier videos. And then, let's see, make sure I didn't forget anything. And then capital T is the final temperature that you want it to be. And little t is your time in minutes. So let's go and look at example 22. We're cooking alicha, which is an Ethiopian stew. We're going to take it off the stove, and when we do, its temperature is 212 degrees Fahrenheit. Way too hot to eat, so we've got to let it cool off. The room temperature is 70 degrees, and the cooling rate for this particular stew is 0.046. We don't know how long it's going to take the stew to cool to a serving temperature of 100. Alright, so the very first thing I suggest we do is go through this word problem and label what you already have. Again, we're obviously talking about cooling down, so that's Newton's law of cooling. Okay? So, blah, blah, blah. When you take it off the stove, its temperature is 212 degrees. Well, that's its initial temperature, so that's T of 0 right here. T of 0. The room temperature is 70, so that's T of R. And R, obviously R is R. We want to know how long it's going to take to cool the stew to a serving temperature of 100. So this is capital T. So we're trying to find little t, which is the time. So let's plug in what we know now that we've labeled all our stuff. So we have 100 equals parentheses T of 0, which is 212, minus the room temperature, 70, e to the negative 0.046 t power. Looks pretty complicated. However, remember, we know how to solve things by graphing when things get too complicated. So let's do that. Remember, no matter what, y1 is on the left, y2 is on the right. Now, when we type this in our calculator, remember, our calculator does not recognize t, so we're going to have to pretend that's an x temporarily. So x is going to represent time. Also, I have more than one thing floating up in the air, so I'm going to need parentheses around that. And since it's up in the air, I'm going to have to be sure to hit that power key. So I like to just draw out what I need to type in before I actually do it. That way I'm sure to get it right. And I suggest you do the same thing. So now let's go through and graph this. So y equals 100, so that's y1. y2, we've got parentheses 212 minus 70, parentheses again. E, you just hit second, divide, raised to parentheses, negative 0.046 x. Close parentheses, and we're good to go. So let's graph it. Every time we do a new picture, let's hit zoom 6. Nothing shows up. So what I suggest you do, you could zoom out of course, but what I suggest you do is go down to option 0, zoom option 0, called zoom fit. What zoom fit does is the calculator tries to force both graphs on the calculator at the same time. So here's what, obviously that represents my stew that's cooling off. Okay? So I'm going to go ahead and try second count, option 5. First curve, enter. Second curve, enter, and guess. Right here, it looks like there might be a point of intersection, so I'm going to move my cursor there, just like we did at the beginning of this unit. As soon as it's in position, I'm going to hit enter. And it tells me x is 7.62. So again, instead of x, we're going to call that t, because that's what we used in the problem. So that means t is 7.62, and our units, based on our information, was minutes. So what this means is it's going to take about 7.62 minutes for this stew that was originally 212 degrees to cool off to a serving temperature of 100 degrees Fahrenheit. Okay, so once you finish most things, if you get a can of soup and then you're microwaving it or whatever, it's going to tell you, let sit for 2 or 3 minutes to cool off. That's close to Newton's law of cooling being applied. Okay. Now let's go to the next example. So the moment magnitude, capital M, of an earthquake that releases energy, capital E, in ergs. Ergs is just a unit of measure of energy. Can be modeled by this equation right here. So we're told that in example 23, on May 22nd, 1960, a powerful earthquake took place in Chile, which is a country in South America. It had a moment magnitude of 9.5. We want to know how much energy did this earthquake release. Okay, so again, anytime you have a word problem, I don't care what situation it is, what math class it is, before you start doing anything, you need to label the information that's given to you. Obviously, we're talking about earthquakes, so we're going to use this equation right here. So it had a moment magnitude of 9.5. Well, obviously, that's my capital M. We want to know how much energy did the earthquake release. So we're trying to find capital E. I always like to write out what I'm trying to find. That way I know exactly what I'm solving for, okay? That way there's no question I'm actually plugging in. So let's plug into our formula. So we have 9.5 equals 0.291 times the natural log of capital E plus 1.17. Okay, so again, like we did in the previous problem, it looks kind of complicated. This one actually can be done by hand pretty easily, just like the other one could have. However, we have the technology, and we haven't talked about graphing in a while since the very beginning of the section, so let's practice graphing a little bit. Left side's always y1. Right side's always y2. Okay, we're just going to type it in exactly what it looks. Instead of E, I'm going to replace that with an X. Okay, because remember, your calculator only likes X's and Y's. That's the only modification you need to make for this problem. So I'm going to go to y equals, clear out any other stuff that's in there. So 9.5 and y1 and y2, I have 0.291 times the natural log of x. Again, we're just pretending that represents our energy, plus 1.17. Okay, we want to graph that. Every time I do a new graph, let's hit zoom 6. Now, obviously, I have a point of intersection that's going to happen somewhere way out here. So I'm actually going to try to do zoom fit, which is zoom option 0. See if that helps any. It doesn't. Didn't help this time because my point of intersection is still somewhere way out here. So what I'm going to do is actually change my window. Now, again, my energy is represented by X. I'm going to change my X min and X max. So let's change it to say, well, energy is going to be pretty big. So I'm going to change X min to 1,000, X max to 10,000. Let's see if that helps. Still no points of intersection, okay? So I'm going to have to zoom out some more. All right, so let's change this to 100,000. Still no points of intersection. So we're going to try this trick one more time, and then it might just be more effective. So let's change this X max to 1 million, add another 0. Still no points of intersection. So what that means is there's a lot of energy that's being generated by this thing. So let's actually go through, instead of graphing, since we had to go through and zoom out so much, it might just be quicker to do it by hand. Okay? So we're going to kind of regroup. Sometimes this happens. You try a strategy and it doesn't work and it wastes a lot of time. So we just regroup and try something else. So what we're doing now is we're going to start off by trying to get the natural log of E by itself. Reverse order of operation says I need to start off by subtracting negative 1.17 from both sides. Cancel out. So 9.5 minus 1.17 is 8.33. And that's still equal to 0.291 natural log of E. And that's multiplication in there. Okay, so now since we have multiplication, to undo multiplication, we divide. So divided by 0.291, divide by 0.291. Again, use calculator to help you out with some of the easy calculations. 8.33 divided by 0.291 is a big decimal. Okay? So 28.63, I'm just going to round a little bit. So 28.63 is equal to the natural log of e. Now, natural log of e can be rewritten as the log base e, which you should remember from previous videos. So log base little e of capital E. Again, capital E represents energy. Little e is a number, so keep those two separate. And to cancel out this log, I'm going to have to exponentiate. Well, bases have to match. So if I had base E here, I'm going to need to jack up my car with base E on both sides. Once I do that, E and base E are going to cancel out. So capital E just falls down. So capital E is equal to E to the 28.63 power. Now, this is my final answer because I have energy by itself, which I wanted, but if I type this in my calculator, it's going to be a really big number. Let's see what that number is. So I have E raised to the 28.63 power, and it's 2.72 times 10 to the 12th power. This capital E that your calculator shows, it's not the same E that we're using in the formula. This represents scientific notation, times 10 to the 12th power. Essentially what that means is, since this 12 is positive, you're going to move your decimal to the right 12 places. If this number after the capital E was negative, you would move your decimal to the left, however many places it told you. So again, that's scientific notation, which you should know from previous classes. So this is also an acceptable answer. So either one of these is acceptable. These two numbers are equivalent. And that's just a short demonstration of how exponential and logarithmic equations are used to model scientific phenomena. As you take a more advanced science class, I guarantee you're going to see exponential and logarithmic equations pop up all over the place. So hopefully these videos will help you survive when you get there.